Good morning. Welcome back to the Mars Convention. I'm glad to see everybody this morning. I got to know a lot of you. I'm Bob Pace. I'm one of the volunteers for the Mars Society. And we have our first guest speaker this morning. He is Vlada Stamenkovic. And he's going to talk the evolution of Mars and tell us something about himself, too.
Good morning, everybody. Thank you very much for being here. It's hard. It's Sunday morning. I'm proud of you. That's the best way to start it. So, my name is Vlada Stamenkovic. I'm a research scientist at JPL, and I'm going to talk to you about two things today. I want to start again looking at the possibility of life on modern-day Mars and see what we scientifically know, what could be possible, whether we're far off or maybe it might be closer to than we thought, and then show you some exploration tools how to address those questions. So I call my talk Modern-Day Mars Habitability and Subsurface Exploration. Now, my talk is going to be separated in two parts. In one part, we're going to do some science and look at some new things which are really exciting us about the possibility of extinct and also extant life on Mars. And then we'll jump into the technologies, how to address those questions. Now, let's look at an example. And what I want to show you here, I mean, here means, I guess, around here, because I don't see it. And let me know if I have to scream louder, but I usually scream loud. There we go. The interesting thing when you think about Mars is, if you go and look at Mars, you know, there's been right now a heat wave in Europe, and I've read a lot of newspapers writing in Europe. Europe is becoming like Mars, which shows, I guess, the level of not knowing what Mars is like. I know it's different over here, but we know it's a desert. It's very dry, but it's a very cold planet. We see, average temperatures are between 140 and 300 Kelvin. Don't ask me what this is in Fahrenheit. I do not know, but it is very cold. And what's really important is as well that the pressure is very low. It's about 6 millibar, about factor of few up to 100 lower than on the Earth. And the atmosphere has very little oxygen, about 0.145%. Remember, our planet has about a 1 bar atmosphere, 20% oxygen, much more than on Mars. However, we've discovered something the last few years that's really exciting. We've discovered amounts of rocks that contain manganese oxides. Now, that's really exciting for one reason. See, iron is really cheap. When there's oxygen, iron does like, let's go. You build iron oxides very easily. You need very small quantities. Manganese is very difficult. It needs a lot of oxygen in a dissolved liquid state. So you need to have oxygen in dissolved waters, and then a lot of it actually, and then manganese will say like, okay, let's bind together, and then manganese oxides. Now, the interesting thing is when we discovered that, people started wondering, what does it mean? These are old rocks, so we most likely indicate something far in the past, or was maybe the alteration occurring over time? What does it mean? Was there more oxygen on Mars? Maybe because water was photodissociated and hydrogen escaped and oxygen accumulated. What's going on? That's really interesting because, when we think about the Earth, we see manganese oxides only after the so-called Great Oxygenation event, which occurred about 2.4 billion years ago, where we had almost no oxygen, and then suddenly we have a spike of oxygen rising to large levels. And only then do we really see manganese oxides. So we're talking really about a lot of oxygen needed for that. And that was a big puzzle. Now, what we did is we said like, well, does it maybe infer something about the potential habitability of past or modern Mars? And to answer that, we said a very simple question, and that's explained in this diagram, and we're going to look at it in a moment. Now, imagine the first question. Can there be liquid, any kind of liquid on the Martian surface or shallow subsurface? Now, we've been debating this thing for a long time. For water, for pure water, it's very difficult because the pressure is very close to the triple point where it becomes very unstable. In the shallow subsurface, if you have a little bit of soil, it can be stabilized to some degree. But what's really important is, because the temperatures are so low, you really need to somehow find some form of brines, which means water and salt mixed with each other, that help you suppress, lower the freezing point of that brine. Now, some salts, when you add some salts to water, you can very much suppress the freezing point. We see this always in winter when we drive around, not in LA, but if you go to the East Coast, or you have to go to the East Coast like in January, February, you see all the slurry streets with salts in there that help to prevent the ice from freezing. That's the important part. Now, what we show in this diagram here is, if you look at different salts, and they're shown in different colors. Example, you take just normal table salt, NaCl, or you take example exotic salts, which are more common on Mars than on the Earth, like perchlorates, calcium perchlorates. This is the CaCO2, CO4, and the magnesium perchlorates, which are just the second and the third one. Sorry, I have to bend over to see the image myself. We can ask ourselves the question, if we have such a brine, how much oxygen in equilibrium with today's atmosphere could be dissolved in those brines? And what we can do is we can generate a chemical model that calculates that. And that's what we've done here. And what is interesting is the following. Let's have a look now at the calcium perchlorate, which is the second one from above. It's kind of like the pink color. You see this here showing you as a function of temperature, the concentration of oxygen you would get today in that brine, in equilibrium with the atmosphere. We're starting at 0 degrees Celsius, which is 273 K, and yet now follow the pink line. You see it goes a bit down, and then it starts to increase. So you start at lower temperature, because when you are at very low temperature and still liquid, the gas wants to stay actually in the liquid and not in the atmosphere. It goes into the liquid and stays there. So we start to have larger concentrations of oxygen. And if you go down, follow that pink curve to about 200 Kelvin, you'll see you reach levels of 2 to minus 4 mole per cubic meter, which is quite a large concentration of oxygen. Now something additional comes in. You see, after I've made the line dotted, not solid anymore. Dotted means always, we scientists do dotted when we're like, oh, something weird's happening, but it's possible, very likely. But, there's a possibility, maybe not. Experiments have shown one thing. They've shown that calcium perchlorates and other brines can very effectively supercool for long periods of time. Even when they're mixed with regolith, that's analogous to example Mars, even when they're mixed with other salts, they still remain for very long time scales just liquid. And this has to do with that perchlorate ion. It's a very aggressive ion that's disturbing actually nucleation freezing. So experiments have shown that for perchlorates, it can remain in a supercooled state down to 140 Kelvin. And if you then say that, okay, let's do that. Let's calculate then the solubility in that liquid. You continue that pink line in a dotted pink line, and you get even larger values of oxygen solubility. So what we learn here is for many brines that can exist on Mars today, in equilibrium with the atmosphere, where there's only little oxygen, you can actually dissolve large quantities of oxygen. Now, how large and how meaningful is that large? Let's look at this next image. Now let's take this data and say, well, let's look at Mars. Let's take the temperature variations we have on Mars between 140 K and 300 K approximately, take average pressure, and let's calculate the solubility range that will be possible on modern-day Mars for different brines. And again, the colors here represent the range for different brines. The important thing here to see is there's two cases. One is the BE, which means no supercooling. We just say like, supercooling is too crazy, let's forget about it. And then there's one that's without the CSC, and then B is with supercooling. We say, well, supercooling, we see it in experiments, it works, so let's trust it. But what's really important is all this, both cases where we see the range of the oxygen solubilities, in the last figure you see it in relation to what we know from the Earth. Microbes need about 10 to minus 6 mole per cubic meter for not just breathing, but for full respiration and reproduction. So if they have more than 10 to minus 6 mole per cubic meter of oxygen dissolved in water, they're happily living. And every brine that we simulated for current Martian conditions has at least 1 to 2 orders of magnitude, even in the worst case, more oxygen dissolved in them than needed for microbes. And we're talking about simple microbes, like E. coli breathing oxygen. We're not talking about something crazy that's living in a weird geyser area. It's like just something really that is everywhere around us. Now, what's really interesting as well is, if you look at the supercooling stage, so the BE case, the first one, where we account for supercooling, the concentrations are large enough that even cross the threshold for sponges to breathe. And sponges are the simplest animals on this planet. So what this shows is, and that's the amazing thing, for decades, people never dared to think that Mars might have the possibilities of having environments that have large oxygen concentrations. It was just not a question. When we thought also about habitability or life, aerobic metabolism was simply not considered because there's little oxygen in Mars' atmosphere. But when you start thinking that bugs, they need actually oxygen dissolved, and you do the calculation step by step according to the laws of physics, you see, wow, actually Mars is a really intriguing place for aerobic respiration today. And the cool thing is, these results help you as well understand these manganese oxides maybe. They don't mean that there's much more oxygen in the Martian atmosphere. It just means there's brines out there, which means there's liquids actually, not far away from the surface. And those liquids can dissolve a lot of oxygen, enough for life to breathe. Now we can do the next step, we can say, okay, let's go to today's Mars. We'll make climate models. We'll look at the average temperature, average pressure as an example. Here are maps of current Mars, climate models, GCM, showing average temperature, average pressure. Let's take this and combine this with the solubility results, because solubilities depend on temperature and pressure. That means if we know what the temperature and pressure on a spot are, we can compute also the solubility at that spot. And when we do that, we get cool stuff. We get maps that show us how the solubility of oxygen can vary on the Martian surface today. Again, two figures. The upper one is with supercooling, we allow for the possibility. The lower one is no supercooling, we ignore the possibility. But what's important, we start to understand where on Mars we can have larger potential for aerobic respiration today for both cases. And they're mostly driven by lower temperature and high pressure regions. The next one we can do, we can say, wow, cool, we know about nowadays Mars, but you know, Mars, let's learn something about time, about evolution. And the important thing here is we can say, well, we know that Mars obliquity, so it's tilt of the axis tilt, is actually changing over time. And it's been strongly changing over time. And if it changes, the climate is affected. And so I show you example here, two pressure temperature plots for Mars on average, annual averages for different obliquities. And now what we can say is, well, let's compute then how the oxygen solubility changes the function of obliquity. And this is, let's look just at the upper pink curve, which shows you the maximum possible value on Mars of oxygen solubility. For low obliquities, it's very large. For higher obliquities, it becomes much smaller. And the variation is by orders of magnitude. And what this shows you is simply, when you go to larger obliquities, the poles start turning towards the sun, start to heat up, and the cooler regions start to become warmer and dissolve less oxygen. But what's really cool is, in the next step, we can now say, well, now we know how actually solubility changes with obliquity. Do we know how obliquity changes as a function of time? We do to some degree. So we can take a model how obliquity changed in the past and might in the future, back 20 million years, and in the future up to about 10 million years. And this allows us to understand then how the obliquity impacts the solubility as a function of time, and therefore how the solubility of oxygen has varied as a function of time. And again here, the upper curve actually shows the maximum value possible, and the lower curve shows the average. And what we see over here, and that's an interesting thing, if you go back, today is 0. You go back to minus 5 million years, we're now in an epoch where there's large oxygen solubility is possible. If you go the preceding 50 million years, 5 million years, and back to 20 million years in the past, then they're about 200 to 1,000 times lower. So what we see is climate change driven oxygen solubility and aerobic potential on Mars as a function of time. And that is the cool thing. We start to understand that Mars has today, and also in its past, recent past, the potential of enabling actually environments that have enough oxygen to be resources for aerobic organisms, or maybe to some degree even habitats. And we know where they could be and how they evolved as a function of time. Now, let me see what time it is. Oh, it's good timing, perfect. So the first part of the message is, wow, Mars is actually much more interesting for extant life than we ever thought. But it's not for life as we thought of. It's for a different kind of life. Life that's actually closer to us than we thought. We've been looking a lot for a very alien, weird kind of life that, you know, doesn't do any aerobic respiration. And maybe it's more similar to that than we actually thought. And Mars today is becoming more and more interesting for those questions. Now, but how do we now go to Mars and explore this, you know, One thing is making a model and comparing with data. Second thing is really going to those places and checking them out. Well, first, those results I've shown you right now are valid in brines. Those brines are stable mostly in the subsurface. They're stable in a shallow subsurface, but also in a deeper subsurface. Example, if the results of liquid water below the South Polar Lake deposit were to be correct, then we would have the potential in those deep environments to have a lot of oxygen because of the lower temperature and also a large amount of possibly perchlorates, if there is an exchange with the atmosphere or there's radiolytic production of oxygen. So what we have to do now is we have to say, like, well, can we explore in those subsurface regions? And can we finally develop the technologies and the strategies, especially because the technologies are already there many times, to finally go back to Mars and look at the really exciting zone, which is not just a micrometer below the surface, but is actually deeper. Can we finally change the dogma and not just, do great science on the surface, but go to the next step, which will allow us to really answer the questions that the Vikings tried to answer more than 45 years ago. And that's why the subsurface is so exciting. And that's shown here with this image. Anything that's related to liquid water or brines or even ices, anything that's related to life, and of course in the future also the resources, happens in the subsurface, shallow to deep. If you're thinking about water stability of pure water, theoretically that's somewhere in the order of kilometers actually. If we have brines, we can bring it closer to the surface. But we don't really know. We don't really know whether really water is there. We have indications, but we haven't really explored it yet enough. But another thing is, if you're looking what we know so far from the subsurface, these are some results, some pictures from MSL taking drill samples that are 1 to 2 inches. Now, the amazing thing I love about this picture is when you look at the surface, the sort of sand that's right above it, it's all the same color everywhere. So these samples have been taken on different spots, kilometers away. But you just go 1 to 2 inches below the surface and the color is different. Now, we scientists get really excited about colors. And the reason why is colors indicate usually the oxidation state. Is it reducing? Is it oxidizing? And that's what life thrives upon. It's redox gradients. Where do we have oxidizing agents? Where do we have reducing agents? And we don't see that when we look at the surface because it's the same stuff more or less. It's immediately oxidized. But beneath that surface lies a world full of wonders which we haven't really explored yet, which is relevant and critical if we are really keen on understanding the potential of life. Now, we have indications that the subsurface might be very interesting. I've just shown you some results. This is my virtual laser pointer right there. On the right side is my map for oxygen solubility, indicating that the shallow subsurface, near surface might be very interesting for aerobic respiration. We had Chris Webster, also from JPL, just published his papers a few months ago about methane seasonal variations, which is really interesting, indicating either volatile sources, clathrate, or maybe even some questions related to life. We've had just now Mars's paper debating and claiming that might be a possibility of liquid, briny, likely perchlorate waters, 1.5 kilometers. That's 1 mile. I'm getting now a bit better. Don't ask me how much in feet. But below the South Polar deposits, we are seeing also RSLs, which are still to be debated whether they're really actually indicating water, but that's something up in the air. But we see some trends, some questions that retain and indicate that water might play a game in the shallow to deep subsurface. Now, also next to just understanding questions related to life and water, I know a lot of people here are excited about human exploration, and it's very simple. Unless we really figure out what the water inventory, icy and liquid, and also methane and the subsurface is about, any mission to Mars will be a horrible Big Brother TV show where we're just going to watch people die. We have to understand questions about where do you get water, where is it poisonous, and we can answer those questions, but we must do that. Otherwise, any human mission is just a suicidal mission. On the second hand as well is for us scientists who are driven by understanding life on Mars, we want to understand that question much better before we send humans. So we have to find and explore the Martian subsurface as soon as possible to enable humans, but also to answer the biggest question that's driving mankind, and that's, are we alone or not? And for this, I want to just show you quickly, I got some time left here, perfect. I want to just show you quickly what we're doing at JPL to address this question. We're starting to explore and build up a program called MarsX, which stands for Mars Subsurface Exploration. I'm really all about acronyms. It's the most important thing, I think, in science at all. And you'll see more. So MarsX is composed of two technologies that we're investigating and developing at JPL in the next few years. One is called Thor, TH2OR, which stands for Transmissive H2O Reconnaissance. And the other one is ASGARD, which is a longer abbreviation. It's for Aerial Subsurface Great Access and Research Drill. And the important thing is, what we really want to do is you want to go back to the, to the daring claims of the Vikings who went out there to, literally look for some bugs. Were the only mission to land on Mars that really looked for life, or metabolic activity to be precise. And we thought, the Vikings haven't completed the mission, and in order to complete them, we, gonna go back to Thor. And what Thor's gonna do, I'm gonna talk in a second, is look where liquid water is, and look what its salinity and chemistry is. And Asgard is a deep drill to access these zones. And it culminates in Asgard because ultimately the Vikings only will find peace once they complete the mission, and then they can go to Asgard and to Valhalla and drink meth and be happy and be like done forever and like let us go now and don't bother us anymore. So I want to talk a little bit quickly now about the Thor concept, which is the one I'm leading at JPL, mostly involved with. It's the transmissive H2O reconnaissance. And what we really want to do is we want to demonstrate that we can develop small, about 5 kilogram units, very low power, 10 watts, that can actually be put down on the Martian surface and can tell you whether there's liquid water anywhere down to about 5 to 10 kilometers, and then tell you also the salinity of the water and therefore infer indirectly the chemistry. Now, the cool thing is we can do amazing science with very small gadgets. And the principle we're doing over here, I'm showing with this image, is just we're using simply electric conductivity. If there is any electric conductive object in the subsurface, and water, example, liquid water is a very good electric conductor if it has a little bit of salt, just a little bit, a hash of salt, and every water has a hash of salt, a little bit of salt. What happens is, if you put some kind of conducting system on the surface, a wire or something else, you put a current through, you switch a current off, it generates a variable magnetic field. Faraday's law of induction says that variable field will induce currents in conductors, example, water's down there, and there we create new variable magnetic fields that go to the surface, which we can detect. And that allows us to find those gadgets. That's different to radar, because radar is setting on a wave, and it's looking at the wave propagation and the wave interacts with the rock, and that's being reflected or diffused back. And here we're actually triggering and trying to understand electric conductivity. That's what we're measuring. Now, the cool thing is, if you're looking at potential challenges, these kind of gadgets exist. They're the most common tool to look for water actually on the Earth, but they're very heavy. They're about 100 kilograms, they're about 50 to 100 watts. They're very complicated, take days to just look at one data point. They're always human-tended, there's a lot of people involved in them. Mars also, is a special environment where there might be actually false positives like magnetite and so on, which we might have to take out. And also, this has never been flown on any planetary mission. It's only done on the Earth. So what we want to figure out, and what's great, Mars is actually the ideal place to do these kind of things. And I'm showing this actually here. Because Mars is cold and predominantly dry, the contrast between dry and wet at this lower temperature is much larger, orders of magnitude. Therefore, for the Mars conditions, we can actually penetrate with much smaller power, much deeper, which is the huge advantage. And by doing so, we'll be allowing ourselves to actually do amazing small missions that will be able to look if there is liquid water on Mars and infer its salinity and therefore also its chemistry to some degree. But what I find also really wonderful is we're developing very small tools, very simple tools that are very cheap, hopefully when we finalize them, that we can actually share with the world. And one of the biggest problems of the world is actually water availability, also in California. And the problem is mostly because large companies are interested in large water sources, but not in the small ones. Now, if you have a small gadget, that costs like $50 and you give it to a village and they can just say like, well, we found water at this depth. And now comes the point, that's not too saline, because if it's too saline, it doesn't work for them. The money needed to desalinate it is too large. So it's drinkable, but it's a quantity that, can give our village, 5 years of water. That's great. It's great for them, not for our company, but they can live. And that's something what I love, because we can utilize this technology not just to bring us to Mars and to understand the biggest question, if there's water on Mars, there's life on Mars, but it can help, you know, our brothers and sisters on this planet who need it the most to actually make it. And also, the technology can be then utilized later on for exploring Europa, for exploring also the moon, for understanding other questions related to ice, water, and the structures. Now, I will not talk anymore, my time is out of the way, about Asgard. I'm happy to talk about it later on. What I want to really give you as a message over here is the following. When we think about Mars, and I have a good dear friend of mine says it over to JPL, says Mars is not a small Earth, it's a different planet. And you have to think differently. And that's what we're seeing here. By looking, example, at the aerobic potential of Mars, we see great surprises, which we never expected, because we always think terrestrial, we think from our perspective. But suddenly we see something emerging, aerobic potential. We see that life might have actually more chances on Mars today than we ever thought. And that's calling for exploration. We also see that we need to explore the Martian subsurface if we want to really answer those questions. We got to push for that. We can't go on with the status quo forever. It's just not interesting enough anymore, and it's not actually helping to answer the question. If we want to make the money we put in useful, we got to ask different questions and use different technologies to answer those, and specifically look in a different domain, which is the Martian subsurface. We do have the tech. We're there. We're developing it. Most of it is ready. Chris Sack, my friend and colleague over there, is going to talk later on as well about drilling technologies, which he's been doing for decades and decades. No, he's not that old. He's still young. and it's there. We just have to literally, only thing I'm going to do is dare and do it. And to give you that, you know, if we manage to do that, well, that's the only way we can finally answer these big questions. And here, in honor of a great musician who posed this question a long time ago, is there life on Mars? We can answer that. We just have to go there.
And her daddy has told her to go.
Thank you very much.
But her friend is nowhere to be seen.
Use this.
Yeah.
Hear me.
So while we're waiting for this, I want to just highlight at the last slide here.
Sorry.
If you have any questions, please feel free to write me. We also have a HU session this year called the New Mars Underground, focusing on Mars subsurface exploration and for answering these questions. And we're building, starting headquarters at JPL, a community that really wants to go and explore the Martian subsurface and get cool stuff. Yes, please.
Okay, so you know that in the 1980s, Tom Gold, the famous geophysicist, demonstrated the presence of a deep hot biosphere under a igneous old crater formation in Sweden. You expect to be able to, and he got borings done, and they brought up this material that was kerogen, and it had life associated with it that nobody expected to find except him. You expect to be able to, with your detection instruments, detect something that deep or that active?
Well, let's say it this way. Know the paper, love it. I do have to say, you know, the interpretation, whether that kerogen is detected is really part of abiotic or non-process is still to be debated. But I fully support the messages that he was trying to transmit, which is the potential of a deep biosphere, which is fully unexplored. And there's a great bunch of scientists, a great team all over the world that's really addressing these questions. We are trying to explore the deep biosphere and how much life can actually originate in the deep biosphere. Maybe it doesn't even need to surface. For Mars, I have to tell this one, we just don't know. We really do not know. Many times I tell myself, if you have a very effective isolating and low resource biosphere that's in the subsurface, if it's very well utilizing resources, you don't really see many signs above that habitable zone. You don't see it on the surface. So we can't even say what's on Mars. Now, the question, can we address these things? Yes, we can. I think, good old times. Yes, we can. I think we can access these domains technologically, and we can sample, and we can make the analysis we need to do to infer its redox potential, its chemistry, its metabolic potential, and also maybe the existence of biomolecules, and also maybe even metabolic activity. So yeah, we can do that.
So there was something at the surface that indicated it was there, which was an old crater formation.
Yeah, well, that was allowing you to see the methane seeping out and see where it is, which brings us to the images of methane seasonal variation I've put in. Of course, that is something which I find might be an indicator to see and explore.
Thank you.
Thank you.
Okay.
Do I choose or?
No, I bring them to him.
Okay, speculation and personal opinion. In the heyday of Mars, when they had the big ocean in the northern hemisphere and more temperate, climate, how far did life advance from just single cell organisms?
Well, see, I have to say, like, I hope this was the case in Mars. I think scientifically it's hard to say that really was there. There's a lot of discussion about the much colder Mars. You see, even the results we have now, we should not always think, Earth-like, humid, a lot of oceans is the ideal thing. What I'm showing you example is, even at low temperatures, you can have conditions which might be actually helpful for life, different kind of life. But, so we don't need to have, very warm past and an ocean to have life. Now, leaving that apart, let's say life maybe evolved easier in the past, it was maybe warmer, we don't know. I've interacted a lot of people to origins of life, great scientists, beautiful people, and I have to say it's impossible, I think, right now to quantify that, because we don't understand we can't quantify processes that relate to the origin and evolution of life well enough. But if we're looking at the Earth, once there was enough oxygen, we see a huge desertification and huge quick change of very simple organisms to very complex organisms. So oxygen might be indeed linked to actually speeding up evolution, giving more potential for actually different kind of organisms. So that might be, having especially aerobic environments, might be an interesting trigger to start asking the question, does it help to boost evolution?
Question?
Yeah. Have you or anyone else done, or are there any plans for simulations of making these solutions and seeing how well bacteria or other microorganisms thrive in them?
Hell yeah. Yes, absolutely. Absolutely. We still don't have results yet to say that. We're going to be doing now tests, and we'll continue this in 1 year to really do the experiments, whether these brines are really stable, how the stability changes, and then putting different kinds of bugs in there and microbes, and seeing how the metabolic activity and survivability changes for variable concentrations. And it's really exciting. Specifically, we're discovering more and more how so perchlorates are not very common on the Earth for what major reason. They get quickly washed away. Earth is really the water time scales are very low here. Things go fast, which is good for us. So when we create mess, we can get rid of it quicker, which we do. On Mars, it's much slower. So perchlorates occur and can be formed in oxidizing environments. There's still some degree of uncertainty to that. But in oxidizing environments where there's low water, but water has to be there, but it's slowly flowing, and that's Mars. So perchlorates can accumulate over there. And they create then this weird different chemistry you don't really see on the Earth naturally. But, and that's now thanks to us humans, we see this kind of chemistry occurring in a lot of waste sites where we just throw stuff out, which is, perchlorates are often a waste product of many plants. And in these waste sites, we see now interesting biochemistry occurring. We see organisms thriving, doing weird oxidation and reduction sometimes of perchlorates and oxygen, giving it forth and back. We see that is actually occurring, but we haven't really explored it yet because it's not naturally happening on the Earth that much. We're just starting. So kind of funny, Mars and waste sites on the Earth come together.
Over here, 45 degrees to your right. So on that notion, how do we know how deep the toxic perchlorates go, or do we need Mars X to tell us?
Well, we don't know. See, this is the whole thing. We've so far you said toxic. Maybe they're toxic for us for sure. Maybe they're not toxic on Mars. We don't know. Right now, we have the best evidence of perchlorates was really Phoenix. some years ago already now, when they digged in the scoop and then they found some evidence of manganese and calcium perchlorates. We have some evidence from orbiters, but from orbiters, we really see literally a micron. We see like what's right there reflecting, what's right there emitting, and that's just the uppermost layer. So we don't know. We really don't know. That's exactly. I have to really say I find it always, when you talk about the Martian subsurface, I'm very serious when I say that is another planet than we have explored in the last 45 years. That's the best analogy we can make. We literally have another planet in the solar system that we've never looked at. And that's the only planet that is in near reach where we can really answer the questions of extinct and extant life. So it's right there. Let's go and get it.
Again, thank you. That concludes the evolution of Mars by Vlada Stamenkovic.